All right, this is part 2 of the practice test for the Math 136 online final. So this is a composition problem. It says for f of x equals x squared plus 4 and g of x equals square root of x minus 1, find the following composite functions and state the domain of each. So we want to do f of g, which remember means f of g of x. So you're putting g of x inside of f of x, g of f of f, and g of g. So when you start out, you want to write the function you see first as a blank shell. So you want to think of f having its x missing. So blank squared plus 4. We're going to fill the g function, square root of x minus 1, into that missing spot. So then this would be just x minus 1, since square and square root cancel out, plus 4. So this would be x plus 3. So that is as simplified as we can get that. Now, your domain is two-part when you do a composition. It is the inside functions domain intersected with the domain of the final answer. When you deal with a square root function, you have to make sure that the inside of that stays greater than or equal to 0. So this has a domain x greater than or equal to 1. A polynomial like this linear equation is all real numbers, so there's no restrictions there. But when you look at them together, you have to say, what do those two answers have in common? Well, they have the x is greater than or equal to 1 in common. All right, so let's do g of f. So we're going to be taking the g function as our outside part. So that's going to be square root of blank minus 1. And we're going to plug the f function inside there. So that's x squared plus 4. Drop the parentheses, and that would just be x squared plus 3. So the inside function has a all real number domain again, because this has a polynomial for the inside function. The other function, we have to make sure this stays greater than or equal to 0. This is the end result. And if you move over the 3 for a second, that's negative 3. X squared will always be bigger than any negative number because we're squaring. So this is also all real numbers. There's no restriction here. So if you have all real numbers for both pieces, which I didn't write my answer yet, this is square root of x squared plus 3, then the domain choice for all real numbers, since both are all real numbers, you would say that that is the domain of the composition. So that is that second choice right there. Okay, f of f means that we're going to plug the, remember, x squared plus 4 with x missing, and then we're going to plug x squared plus 4 into the missing x spot. So we need to FOIL that out. So x squared plus 4 times x squared plus 4, and then we have our plus 4 at the end. This is x to the 4th plus 4x squared plus 4x squared would be 8x squared plus 16 plus 4. So this ends up being x to the 4th plus 8x squared plus 20. The original function was a polynomial, so all real numbers. The final answer is also a polynomial, so this one again is all real numbers. Probably the trickiest domain is the last one. This is g inside of g, so that would be square root of blank minus 1, but our function inside is also a square root. So we have to deal with the domain x greater than or equal to 1 because of the inside function. We can't really combine these at all because they're this part right here is under a radical, so you can't subtract it from the part that's not under the radical. But if we set that whole piece underneath there greater than or equal to 0, like this, we're trying to find the domain of this outer radical. If you add that 1 over, and think about it just as an equation for a second. If I square both sides, this would be x minus 1 equals 1 squared, which is 1. So x equals 2. So this will equal 1, or this will cancel out to 0 if you want to think about that when we're at 2. You can't go smaller than that because if you put in a 1 here, you're going to get 0, square root of 0, which is 0. 0 minus 1 is not greater than or equal to 0. So we have to use that our x's have to be greater than or equal to 2. Since that's where we equal the 0 and we want to keep it bigger. And then this answer would have just been square root of x minus 1 minus 1. Okay, that moves us on to number 9. This is also composition, but we're doing evaluations. So for that first guy, you're doing f of g of 4. So you first want to do g of 4, which is 3 minus 1/2 times 4 squared. That would be 3 minus 1/2 of 16, which is 3 minus 8, which is negative 5. This answer goes in for g of 4. So now we're doing f of negative 5. So come down here, f of negative 5 is 5 times negative 5 squared minus 4. 5 squared is 25 times 5 is 125 minus 4. So that's 121 for that first blank. Okay, now we're going to do g of f of 2. So g of f of 2. So start out with f of 2. That would be 5 times 2 squared minus 4. That is 4 times 5, so that's 20 minus 4, that's 16. Now we're going to plug 16 into the g function. So this is 3, I'm going to work it right here, minus 1/2 of 16 squared. 16 squared is, I believe, 256. I'm going to double check that. 16 times 16, yep. Take half of that. That's 128. So this is 3 minus 128, which is negative 125. Okay, f of 1 means we need to start first of all with f of 1 on the inside. So f of 1. F of 1 would be 5 times 1 squared minus 4. So that ends up being 5 minus 4, which is 1. So that's just a quinkydink. You also are going to be plugging 1 into the outer function, so it's going to equal 1 again because it's the same function. G of 0. Oops, I'm running out of room. So we need to do g of 0 first. So g of 0 is 3 minus 1/2 times 0 squared. That's just going to be 3. So now I'm going to plug in g of 3. So 3 minus 1/2 times 3 squared. That would be 3 minus 9/2. Get a common denominator. That's 6/2 minus 9/2. That is negative 3/2. So your idea here is that you plug the number into the inside function and then the answer you get gets plugged into the outer function. Okay, some of these next ones are going to take a little bit of time because they are word problems. This one right here is the half-life of carbon-14 is 5,600 years. If a piece of charcoal made from the wood of a tree shows only 79% of the carbon-14 expected in the living matter, when did the tree die? So the problem with this is that this 79% here is not usable yet. We have to first of all figure out what rate is our tree decaying at. And what we know about a half-life is that if you have your formula, future value of some kind equals initial value of e to the negative kt. That's the formula for decay, especially continual decay like this. So what we know is that a half-life is when you divide both sides by a sub 0 to try to get the e by itself, base e, this always ends up being a half. That's true anytime you're doing a half-life. So if you're doing a half-life, when you divide, you get half. The negative k, we don't know, but the t is 5,600. So we need to try to find this rate of decay. And the way to do that is to take a natural log of both sides so we can pull this power to the front. So when we do that, that would be negative 5,600 k times natural log of e. So we're doing the natural log and pulling that power to the front. But natural log of e is 1. You can check that on your calculator. So all we need to do to find our rate of decay is divide natural log of a half by negative 5,600. So 1 divided by 2 is a half. Take the natural log of that, divide that by 5,600 negative, and that is, and you'll have to kind of convert this because right now this is e to the negative 4. So we have to move that back 3 places. Sorry, I'm trying to move my calculator over. Oh, that's too far. So we have that k is going to be 0.00012, and it's going to be negative when we plug it back in because we're going to use the formula we had before, but that is our rate of decay. So this is a very slow decay, which makes sense because your half-life's like 5,600 years. So then that's not the answer. That is just telling us what the rate of decay is. So now we know A of t is equal to a sub 0 e to the negative 0.00012 t. I know it's negative because remember decay should have that negative exponent on it. Now if you had not put that there, you would have gotten a negative answer here. So either way, whether you remember the negative here or not, you'll get a negative eventually. So then this guy, we're trying to figure out when does this divide over and make 0.79. So if you want it to be 0.79, not 50%, like this half-life is 50%, imagine dividing a sub 0 over again, but the answer comes out to 0.79 this time. So then we're trying to figure out how our time is related to this. So we'll take the natural log of both sides, and I'm going to show my work on this one. Natural log of e to the negative 0.00012t. Sorry, my pen has sometimes gets stuck. There we go. Pull that power to the front. So we have natural log of 0.79 equals negative 0.00012t. Natural log of e is a 1, so that guy goes away. And all we have left to do is divide. So this will tell us how many years would it have been, and it should be less than 5,600 because we were at 79% carbon when the half-life was at 50% carbon. So we should expect it to not be as many years in the future. So 0.79 natural log divided by 0.00, oh, too many zeros, 1, 2, and it's negative. That is 1,964 because it did say to round to the nearest whole number. So, you know, in 5,600 years, you would only have half the carbon you originally started with. So to get to 79%, it has to be at 1,964 years have passed. Okay, for number 11, we're putting the logs back together. So the first step when you're doing that is to put the powers in front back up as exponents. So this would be log 3 of u to the 8th plus log 3 of v to the 3rd. And then when you have a plus between them, it becomes 1 log, and you multiply the inside. So u to the 8th times v to the 3rd. And that's as far as you can go. Okay, so let's talk about the next word problem. Strontium-90 is a radioactive material that decays according to the function A of t equals a sub 0 e to the negative 0.0244t. Where a sub 0 is the initial amount present, A of t is the present amount present after so many years, and we want to assume that the scientist started with 800 grams. So we're going to be able to use that in a minute. The decay rate, though, you should be able to pick out. It is the exponent part in front of t, but it needs to be changed to a percent. And it did say include the negative sign. So negative 2.44 if you turn this back into a percent by moving the decimal 2 places to the right. How much strontium-90 is left after 40 years? Okay, so we know that our initial value is 800. We've got our negative 1 point, or excuse me, still on the other problem. Negative 0.0244, and it's 40 years. So this is a direct evaluation since we're looking at a specific time. So 0.0244, I have to do mine a little opposite to probably your calculators, times 40. I'm doing my exponent first. Then I want to raise e to that power. So e, oh, it doesn't let me do that. Hang on. Second, there we go. So let me try this again. 0.0244 times the 40 is this, e to that power times 800. And we're rounding to the nearest whole number, so this would be 301 grams. When will only 600 grams be left? So that's asking you about the future. So 600 left when we started with 800. So when you ask someone for solving for time, instead of giving them time, you're solving for an exponent. When we solve for an exponent, it's going to usually end up involving logs, unless the bases on both sides match, which they don't. Sorry, that's not 8,000, that's 800. And then, so I'm dividing this 800 over because I want to get E by itself so I can somehow use a log to pull this power out. So this would be 6 over 8 if you reduce it down, which is 3/4. Sorry, trying to do mental math. And then this is equal to E to the negative 0.0244 t. Taking the natural log of both sides, that will allow me to pull this power to the front. And then remember we said natural log of E is just 1. So we're just dividing by this. Okay, so let's get our calculator out. So 3 divided by 4 is the inside. Natural log divided by 0.0244, and that's negative. And that would be 11.8 since they said round to the nearest tenth. So about 11.8 years. Okay, so when would the half-life be? Well, the half-life would be when you have 400 left over, when you started with 800. Divide over the 800, so you're going to get 1/2 equals E to the negative 0.0244 t. Again, taking the natural log of both sides, that'll allow you to pull the power to the front. And natural log of E would be left over, which we said is 1 anytime we have that. So we're dividing by this again. So natural log of 1/2 divided by negative 0.0244. So 0.5 or 1/2 natural log divided by 0.0244 negative. That is 28.4 years. Okay, which leads us to number 13, solve this solution. And this is another one, bring your power to the front. X times natural log of E equals 9. We learned that natural log of E is a 1, so X equals 9. That one is a super simple, just seeing if you know what natural log of E is. Okay, for the last one on this video, number 14, we're doing another word problem. It says the population of a colony of mosquitoes obeys the law of uninhibited growth. Now, uninhibited growth means the future value, A of t, equals A sub 0 e to the kt. There's no negative this time because it's growth. If there are 1,000 mosquitoes initially and there are 1,500 after 1 day, what is the size of the colony after 2 days? So the first thing we want to do is figure out the growth rate. So we're going to have to plug in 1,000 for the initial value. We're going to put in 1,500 as a future value, and that future value happened when we had a t-value of 1, because it was 1 day. So we need to, first of all, divide over the 1,000. This would be 15 over 10 if you cancel the 2 zeros, which reduces to 3/2, e to the k. We'll take natural log of both sides. We get k times natural log of e when we pull the k down. That's a 1. So we just need to do the natural log of 3/2 to find our rate of growth. So 0.4055. Now, that does not answer the first question because they want to know how much is there after 2 days, but that allows me to rewrite my formula. I now know that A of any time is 1,000 mosquitoes, because that's our initial value, times e to the 0.4055 t. So if I want 2 days, I just need to plug in 2 for t. So 0.4055 times 2. We're going to raise that to that's going to be our power on E. times 1,000. So it looks like we would have 2,250 since we're rounding to the nearest whole number. And then how long until it is 70,000 mosquitoes in the colony? So 70,000 is our future value. We know 1,000. We're trying to find the time. Sorry, I don't want a negative there. 0.4055t. Anytime you're solving for an exponent and the bases on both sides don't match, you're going to be using your natural log or your logarithms. I'm going to divide by 1,000 first. So that was going to make that 70 equals e to the 0.4055t. And hopefully you're kind of seeing a pattern. We take the natural log of it. On the other side, that just leaves us with the exponent because you have that natural log of e once you've pulled the power to the front. So we're just dividing this. 0.4055. So natural log of 70 divided by 0.4055. That is 10.5 days. So it's only going to take 10.5 days to have 70,000 mosquitoes. That is why you don't want standing water outside, because those mosquitoes multiply really quickly. Okay, so that's the end of the part 2 video, and part 3 will be coming shortly.